Let me teach you how to do the noble gas shortcut. Noble gas shortcut is pretty awesome. It's called I'm actually going to leave that up there because I'm going to show you how awesome this is. So these are called noble gas configurations. You just wrote the full electronic configuration. We're now going to write noble gas configurations. Here's what you do. If I want to write the noble gas configuration for barium, you take the noble gas that comes before it. So barium is element 56. 54, xenon is the element that comes before it. We're going to put brackets. We're going to do bracket xenon. And then 6s2 to barium, 6s2. This is so awesome. Noble gas configurations, essentially, by putting the noble gas that comes before it in brackets, that's like saying, hey, it's everything up to xenon. That's like saying, hey, this is a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. So that's bracket. And then you only write what comes after it, 6s2. And then it's so nice, you can still do the half arrows for what's shown. So I could do the lines and half arrows for the 6s2. It's really not that bad. So why don't we practice this? Okay, so you take the noble gas that comes before it, and then you write everything that comes after it. So for example, why don't you give me the noble gas configuration for bromine? Give me the noble gas configuration for bromine. You got this. All right, bromine. The noble gas that comes before it, argon. And now it's like saying, hey, man, you made it to argon. Let's write everything thereafter. So that's a 4s2, 3d10, 4p5. And again, you can do the lines and half rows now because it's not super messy. S's come as 1, D's come as 5, P's come as 3, up, down, up, 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 down, 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 up, 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 down, down. Woo! How we do? Those noble gas configurations are pretty awesome, right? Let's do one more noble gas configuration. We'll talk about the D4, D9 exceptions. And then we'll evaluate where we're at. What time is it? 8:45. We're doing good. Doing so good. Oh, my goodness. How about, oh, man. How about ruthenium? Yeah. Ruthenium. All right, that's going to be a krypton in brackets. And then it's going to be a 5s2. And then it's going to be a 4d, 1, 2, 3, 4, 5, 6, 4d6. S's come as 1, D's come as 5. There it is. Woohoo! Hopefully you guys are, how many people did Aufbau before? Give me like a thumbs up if you've done Aufbau before. All right, there's 2, 3 folks. Man, that's not so good. Of those of you that did this before, did you use the periodic table? Give me a thumbs up if you Aufbaued like this before. Or did you memorize the silly, oh, okay, so Lorraine did it like this before. That means you had a good chemistry teacher, Lorraine. That's what that means. All right, let's do the D4 and D9 exceptions. The D4 and D9 exceptions. Oh boy. D4 and D9 metals don't exist. They steal an electron from the previous S orbital and become D5, D5s, D5 and D10s. I will explain. Write that down. D4 and D9 exceptions. D4 and D9 metals don't actually exist. They instead steal an electron. It is more stable for them to steal an electron from the previous S and become a D5 or a D10. Write it down. We'll talk about what it means.
Yeah, I have a quick question. Going back to the noble gas configurations, what if it's a noble gas? Like, would you just put the previous noble gas, or?
Nah, you still got to do that. Oh, that's a great question, Elliot. Yeah. So here's Elliot's question. What if I asked you to write the noble gas configuration of krypton? So can you do krypton in brackets and move on? No. Sorry. Everybody wants to do that. That'd be pretty great if you could, but you can't. You got to do the noble gas that comes before it, argon. And then you'd have to write 4s2, 3d10, 4p6. That's a good question, Elliot. People always mess that up. Yeah, even if it's a noble gas, you still got to do the noble gas that comes before it. All right, folks, let's do this D4 D9-age. Oh man. Let's do, oh my goodness. Let's do the noble gas configuration of chromium. You would think. So first of all, chromium, noble gas configuration. That's going to be argon in brackets. Pop an argon in brackets. And then you would think it would be a 4s2, 3d4. S's get 1, D's get 5. And you would think it would be this. Go ahead and write that down. This is wrong, but it's okay to be wrong. Here's what it does. D4s and D9s don't exist. So it's not stable. Here's what they actually do. They steal an electron from here. And they send it out here. So this guy gets stolen and sent to here. So it's not actually an S2D4. It's an S1D5. D4s and D9s don't exist. They steal an electron from the previous S. They use it to, in this case, half fill, or in the case of a D9, totally fill the D subshell and do that. Why do they do that? Scientists still argue about why these elements do this. Okay, but for some reason, and they have some ideas we're not going to get into, it's more energetically stable to do this. So I would like you, with this knowledge, to try copper. Try copper. That was chromium. Try copper. Copper. You can do noble gas. I don't know if I mentioned noble gas or not, but you don't have to write out the full, man. Boy, these summer 6-week chem classes, man. Crazy. In one night, we're covering like what I would have done in like 2 weeks, man, or like at least a week and a half during the normal semester. It's just crazy. Argon in bracket, you would think it would be a 4s2, 3d9. But it's not. It steals an electron because D4s and D9s don't exist. Pops it out there. It's actually an S1 D10. S1 D10. Cool. Molybdenum. Go and do the same thing. Molybdenum is not a 5s2 44. It's a 5s1 45. And silver. Silver is not a 5s2 49. Silver is a 5s1 4010. I know what you're thinking. Wait a minute. Do tungsten and gold do a similar thing? They do, but you don't have to worry about it. because that's past barium, and we're not going to do that. So you don't have to worry about that. Awesome. Let's tie up some other loose ends. So those are the D4, D9 exceptions. What else is there? Now, we're going to do that in a minute. Let's talk about Pauli's exclusion principle. Pauli's exclusion principle states that two electrons in the same orbital must always spin in opposite directions. Pauli's exclusion principle states that two electrons in the same orbital must always spin in opposite directions. This is why we show an orbital like that, and we put the electrons in it like one pointing up, one pointing down, half arrow up, half arrow down. That's a representation of Pauli's exclusion principle. Why is this, though? Well, we got to talk a little physics here, folks. This is easiest to understand for a spherical type orbital. Let's imagine that a half arrow pointing up is like an electron spinning clockwise. In physics, what you learn is that a spinning charged particle will produce a magnetic moment according to the right-hand rule. How does that work? All right, I got a job for you. Find your right hand. Got it. Cool. Just put that left hand behind the back. You don't need it. If you curl the fingers on your right hand in the direction that an electron is spinning, your thumb will point in the direction of the magnetic field it creates. Electricity and magnetism go hand in hand. They always create, one creates the other at 90 degrees perpendicular to the other. So electricity is going to create a magnetic field according to the right-hand rule, where if my electricity is going this way, the magnetic field it generates will be going into the board. If my electron was spinning counterclockwise, now I'm going to find my right hand again. Got it. Now it's going to curl and my thumb will be coming out of the board. So you see how an electron going clockwise, thumb into the board, electron going counterclockwise, thumb out of the board. Here's what's going on. If I have two electrons in the same orbital, they have to spin in opposite directions so they cancel out each other's magnetic fields and the atoms aren't magnetized. If the atoms were magnetized, they would be attracted and repelled from each other, and they'd slam into each other, and the world would end, and it'd be crazy. Pauli's exclusion principle gets pretty heavy, man. You can watch some YouTube videos, go down some rabbit holes and stuff. They think that teleportation is possible because of Pauli's exclusion principle. They think that traveling faster than the speed of light or sending information faster than the speed of light is possible because of Pauli's exclusion principle. It's some crazy heavy stuff, man. Okay, that they get into. You know, I mean, I even heard somebody talk about time travel or something. In the fact that you could go into the past. I don't even know. Anyway, don't worry about any of that. What you need to know is that when we put two electrons in an orbital and one is up and one is down, that is to try to represent this phenomena of Pauli's exclusion principle. Okay. Next thing we need to talk about the valence electrons versus core electrons. Valence electrons are electrons in the highest energy level. Valence electrons are electrons in the highest energy level, and core electrons are electrons in all other energy levels. Go ahead and write that down. We'll talk. Okay, so when we write electronic configurations, we can figure out how many electrons are in the outer energy level, how many valence electrons an atom has, and how many electrons are in the core energy level by looking at that configuration. So let's practice this. Let's pick a random easy element here. Now here you're going to have to write, if you want to get the core electrons easily, you'll have to write the full electronic configuration. So why don't you give me the full electronic configuration of silicon? Give me the full electronic configuration of silicon. Go ahead. Full electronic configuration, not the noble gas, no shortcut. Give me the full thing for silicon. So if we do silicon here, that's going to be a 1s2, 2s2, 2p6, 3s2, 3p2. If you did the lines and half arrows, that's awesome. Let's talk valence electrons. You got to find the highest energy level. And the highest energy level for silicon is the third energy level. How many electrons does silicon have in the third energy level? The answer, 4. It has 2 in the third energy s orbital, the third energy sphere, and it has 2 in the third energy dumbbells, okay, the p's. That's a total of 4 valence electrons. Now, core electrons. I'm going to show you 2 strategies. You could add up everything that's left. That's 10. Or you could look at the atomic number of silicon, atomic number 14. So it's got 14 total electrons when it's neutral. Do 14 minus the 4 valence, there's your 10 core. So that's another strategy for getting the core electrons. Sure, man. What else to talk about? Let's do some ions. And then I believe, we'll look at the slides. I'll see, but I think that's pretty darn good. I'm feeling pretty good.
Would you mind re-explaining how you got the valence electrons again? I'm sorry.
Absolutely, no, that's absolutely. 2, 2s2. Cool. The valence electrons, the electrons in the highest energy level. These coefficients are your energy levels. So the highest occupied energy level for a silicon atom is the third energy level. There are 2 electrons here in the 2s, and there are 2 electrons here in the 3. I'm sorry, there are 2 electrons here in the 3s, and there are 2 electrons here in the 3p. So that's 4 total electrons. That's where the valence came from. Does that make sense?
Yeah, that makes sense. And I understand how to get the core ones too.
Yeah, so then the core would be all the lower. Or what I do, because it's faster, take the total minus the valence, and that gets you the core. Which
Yeah,
and using that method, you can actually do it from a noble gas configuration. So that works even from a noble gas, right? So silicon, if we did the noble gas, that would be a neon in bracket 3s2, 3p2. Now you could get your valence, highest occupied level is the third energy level. You could get your valence here, but now to get the core, you can't add them up. You'd have to do the 14 minus 4 to get the 10 core. Yeah. That actually, you just reminded me. Let's do another one of these. We can now explain why the D's are 1 less than the row you're in. They have to be because it would jack up the valence electron count. For example, say I wanted to get the valence electrons for selenium. Let's do the noble gas configuration. If I'm doing selenium, that's going to be an argon in bracket. and then it's going to be a 4s2. Then it's going to be a 3d10. And then selenium going to be a 4p4. You got to be careful here. My highest energy level is the 4th energy level. I have 2 here and 4 here. That's 6 valence electrons. Right? The D's are 1 less than the energy. The energy level for the D's is 1 less than the row you're in because the D orbitals are not valence electrons. You actually drop down in energy level. So you actually go out to the 4th energy level, fill the 4th shell, come back to the 3rd shell, put 10 more in the D's, and then come back out to the 4th shell. So the D's are 1 less than the row you're in because it would screw up the electron count if they were in the same energy level. Valence electrons only go up to 8. And there is a shortcut for getting valence electrons. You can check your work. I'll show you this. It only works for main group elements. If you number across the families 1 to 8, and actually if you use that A numbering system, so that'd be 1, 2, skip the transition metals, 3, 4, 5, 6, 7, 8. Selenium, that whole family has got 6 valence electrons. We did silicon before, that whole family's got 4 valence electrons. So if it's a main group element, you can kind of check your work doing that. Yeah. Let's do ions really quick, and then I think we'll call it a night. Getting messy. Let me clean this up here. We're just doing too much work, man. Good enough. Okay, we'll take it. Let's say I want to do, man, I don't know. Let's say I want to do nickel 2+. And I want to do a noble gas configuration. Here's what I recommend. This is a cation. We're going to talk about what that charge does in a minute. Let's start by writing the neutral, like the electronic configuration for neutral nickel. And we can do the noble gas. So that's going to be argon in bracket. And if this +2 wasn't there, we would do 4s2. And then 3D 1, 2, 3, 4, 5, 6, 7, 8, 3D8. Cool. But now we got a +2 here. What does that mean? That means this guy lost 2 electrons. What are the electrons that are going to be the first to go? What's going to be the highest energy electrons? So the first electrons to go for nickel are going to be these 4s electrons because they're in the 4th energy level. You always remove the highest energy level electrons first. So nickel +2, got a +2 charge. I'm going to take those 2 electrons away. The nickel +2 cation would be an argon in brackets 3d8. Now, what if it was +3? Well, now I would need to take another electron away. And I'm going to take one of these paired up electrons away. And now it would be a 3d7. So hopefully you see how it works with the ions. You take the highest energy electrons first and then keep working. The next highest energy electron would be there. The next highest energy electron would be there. Then you can take any of the 5, right? Because the paired electrons are higher in energy than the unpaired ones. So that's how cations work. You take, anions work by adding, right? So what if we wanted to write the, I don't know, noble gas configuration for the fluoride anion? That's the F-1 anion. So if we wanted to do the noble gas configuration for that, we would pop helium in brackets. Now, yes, you can still use helium. It is a noble gas. Even though we moved it over here, you can still put helium in brackets. And then it would be a 2s2. Neutral fluorine, no charge, would be a 2p5. This is fluoride with a -1 charge. We're going to add an electron. It's a 2p6. It is that we actually have a term for this. Fluoride has the same electronic configuration as neutral neon, right? And we have a term for this, which we'll get to on Wednesday. This is called isoelectronic. Isoelectronic means you have the same electronic configuration. Isoelectronic. So fluoride and neon have the same electronic configuration. Yep. I'm happy with that. That was a good night. Was it 9:11? Still like 40 minutes early.